So, finally, B part 4, lecture 19, the Noether theorem for spatial translation, conserved momentum density. That's, I will emphasize here, this is momentum density. Today is 9, okay? So, let's prove, okay, that first of all, the step 1, you start with the Euler-Lagrange equations. You see, in a field theory with Lagrange density L, function of phi and the partial derivative of phi, the Euler-Lagrange equation reads partial L, partial, this case, partial derivative of this term over here, okay? This is the momentum, you see, I will see later. This is what I want to prove, to show. This equation 1. This equation governs the dynamics of the field phi of x. Remember that x over here, okay, is xi. You see, x1, x2, and x3. No time is involved, since you are leading with a spatial translation only, not time translation. So, this case, let's go to step 2. This is step 1, this is step 2. Assume a symmetry under a spatial translation. You see, we are focusing on the case where the spatial translation are a symmetry. This we did before, you see, xj, you see, this is xj plus, this is a little increment, okay, which in general is constant. So, now this is coordinates, this is the field x minus epsilon. You remember that this phi of x prime, so you just subtract, okay, this increment over here. So this is equal, you can expand this as phi of x minus, you see, this term over here, plus the order, superior order, okay? Now, then you approximate the difference, okay, of this minus epsilon k partial derivative with k respect to the partial derivative with respect to k of phi. You see, just approximate to this minus over here. So let's move to step 3. Symmetry implies partial L respect to phi is equal 0. I want to show this. You see, this implies. See? So, for spatial translation to be a symmetry of the action, the Lagrangian must be invariant under change in the coordinates. So, if you change coordinates, okay, the Lagrangian remains the same. That's a symmetry. That's what we call a symmetry of Lagrangian. This often happens when, you see, L will be function only on this derivative over here, okay? This is analogous when you are involved with classical mechanics. This is analogous to Q dot. You see this one, okay? Q is related to the field, and Q dot is related to the partial derivative of this field over here. So, this implies that partial L respect to phi is equal to 0. This is, attention now, this is a consequence. There's a consequence of Lagrangian must be invariant under change in coordinates. So this is a consequence. Consequence of this assumption over here. So that's it. So Then from relation 1, you see, I set this is equal 0, then this divergence of this term over here will be 0, you see, divergence, I call this Pj. So this is equal 0, which implies that this will be constant. Attention now, the conserved momentum density is the conservation of momentum, you see this case, Pj, under, attention now, this is particular case, under spatial translation, see? So again, Noether theorem proves from symmetry, okay, in this case, the symmetry is a spatial translation, that this leads to a conservation of momentum density. See, that's it. Okay, if you assume a symmetry rotation, this is another game. You see, that's it. Okay.